It begins with a flicker, an anomaly so subtle that it might have been missed by anyone else. In the heart of the vastness, where cosmic observation typically yields the predictable, the astronomers working with data from the latest space observatories saw something that didn't belong. It wasn't a supernova, it wasn't a rogue planet, and it certainly wasn't anything that could be quickly dismissed as interference or noise in the data. No, this was different. This was a signal, faint but undeniable. A galaxy unlike any other ever observed in the observable universe. A flash of something new, something unexplained, that sparked the beginning of an intellectual journey that would stretch the very limits of imagination. The discovery didn't happen with a dramatic, cinematic moment of brilliance or an earth-shattering breakthrough. In reality, it was far more humble. It was a simple observation in the quiet hum of data streaming through a research team's telescope. One of the astronomers, sifting through the immense dataset, noticed a tiny outlier, a faint smudge in the distance. To an untrained eye, it would have been easy to dismiss, just another cosmic anomaly that couldn't quite be explained. But to this astronomer, something about it didn't sit right. It didn't conform to the well-established patterns of known galaxies. It was too distant, too bright, and it didn't align with existing models of galaxy formation. For the team working on the observation, the first thought wasn't excitement but confusion. Was this a mistake? A calibration error? After all, the universe is full of such glitches, small distortions in the data, transient phenomena that could be easily overlooked in the rush of trying to uncover something groundbreaking. But there was something different about this particular anomaly. Something that called out for further inspection, something that triggered the imagination of the scientists involved. They began their work with skepticism, but as hours passed, their curiosity started to overshadow their doubt. They began by asking simple questions. What if this is real? What if this galaxy, this faint whisper in the dark, wasn't just a data glitch but something far more important? The initial analysis revealed a series of unexpected properties. First, its brightness, way too much for a galaxy of its apparent age. Then there was its location. It appeared to be in a region of space thought to be completely devoid of galaxies. The more they studied, the more questions piled up. What they were looking at didn't align with the known theories of galaxy formation, which meant it was challenging some of the very foundations of modern cosmology. As the research team dug deeper, they began to understand the enormity of what they were witnessing. This wasn't just an unusual galaxy, it was something that could reshape everything they thought they knew about the early universe. It was as though the rules governing the birth and evolution of galaxies had been rewritten. The implications of this discovery were so profound that it prompted a frenzy of activity. The team worked through the night, analyzing data, revising hypotheses, and reaching out to other astronomers in an effort to corroborate their findings. The excitement was palpable, and as word spread through the scientific community, a sense of wonder began to take hold. The first major hurdle was confirming the galaxy's existence. Was it real or was it just an error in data interpretation? The team had to employ every tool at their disposal, advanced algorithms, alternative models of galaxy formation, and even cross-referencing with other telescopes and observatories around the world. Every effort, every analysis, seemed to confirm the original hypothesis. This galaxy was real. But what kind of galaxy was it? How could something like this exist in the first place? The more they looked, the more baffling the discovery became. It was a galaxy that seemed to have defied all expectations. It appeared to be older than it should have been. Its light seemed to have traveled from an era so early in the universe's history that it shouldn't have existed yet. This galaxy was thought to be an impossibility. How could such a galaxy form at a time when the universe was still in its infancy? According to everything they knew, galaxies couldn't have formed so early in the timeline of the universe. The cosmic timeline, stretching back over 13.8 billion years, was supposed to have a certain order, a certain progression. Galaxies were supposed to form gradually, as gravity began to pull matter together after the Big Bang. But this galaxy didn't fit that narrative. It seemed to be an outlier, an exception to the rule. As the team analyzed the galaxy further, they were struck by something even more mind-boggling. The galaxy appeared to be far larger than expected for its age. In the early universe, galaxies were believed to be much smaller, their stars in their formative stages, slowly coalescing over time. Yet this galaxy seemed to have formed rapidly, packing an enormous number of stars into an unexpectedly compact space. The discovery was almost like a cosmic miracle, a galaxy that shouldn't have been possible, existing in a way that violated the very understanding of cosmology. How could it be so far ahead of the theoretical curve? How had it managed to skip over the stages of development that other galaxies had taken billions of years to go through? The scientific community was captivated. Word spread quickly about the discovery, and with it came the inevitable wave of skepticism. Critics questioned whether the data had been properly interpreted. Some argued that it was a case of faulty equipment or perhaps an unexpected interference from another source. But the team pressed on, unwavering in their belief that what they were looking at was something truly groundbreaking. As they shared their findings with other researchers, more and more astronomers began to rally behind the discovery, eager to see whether this anomaly could be the key to understanding the mysteries of the universe. The more the team delved into their research, the more they realized that this galaxy was more than just an anomaly. It was a window into a new era of astronomical discovery. The implications of this discovery reached far beyond the confines of this one galaxy. It posed questions that had never been asked before, forcing astronomers to confront the limitations of their knowledge. How could such a galaxy exist in the early universe, and what did it mean for our understanding of cosmic history? How had it formed so quickly, and what did that say about the conditions that existed in the universe's infancy? With each new finding, the mystery deepened. But as the questions piled up, so too did the sense of exhilaration. This was the kind of discovery that could redefine science itself, changing the course of humanity's understanding of the cosmos. It was a spark, a tiny flicker of something extraordinary, something that would ignite a firestorm of curiosity and inquiry, pushing the boundaries of what was thought possible. What began as a single observation, a faint outlier in the vast sea of data, had evolved into one of the most exciting breakthroughs in modern astronomy. The initial disbelief began to fade, replaced by a growing sense of anticipation. What would this discovery mean for the future of science, for the future of our understanding of the universe? The team was standing on the precipice of something extraordinary, an opportunity to rewrite the cosmic narrative, to explore the unknown and challenge the established truths. It was the beginning of a journey into the heart of the universe's deepest secrets. And it all started with a single quiet flicker in the data. What does it mean to identify a galaxy that challenges everything we thought we knew? The discovery that astronomers had stumbled upon something extraordinary didn't just send shockwaves through their team, it sent ripples across the scientific community. As the data continued to pour in, each new analysis painted a picture that contradicted established models of galaxy formation. This was no ordinary galaxy, it was something far more mysterious, something so unprecedented that it could change the way we view the entire universe. In the grand scheme of astronomical discoveries, the identification of a galaxy is hardly a rare event. After all, there are billions of galaxies scattered across the observable universe, each one with its own story to tell. Yet, for all their diversity, galaxies have certain things in common, patterns that astronomers have spent decades unraveling. From their size and shape to the way they evolve over time, galaxies follow a predictable narrative, one that fits neatly within the framework of our current understanding of cosmology. But this particular galaxy was an anomaly, a stark contradiction to the cosmic order we had come to rely on. And that's what made it so remarkable. The more astronomers studied this newfound galaxy, the more they realized that it existed at a time when galaxies were thought to be incapable of forming. This was a period in the universe's history known as the Cosmic Dawn, a time just after the Big Bang when the universe was still a hot, dense soup of particles. It was a time when the first stars had just begun to ignite and galaxies in their current form were believed to be mere fantasies. Yet, this galaxy seemed to have formed far earlier than anyone had anticipated, emerging during an epoch when cosmic conditions were thought to be too chaotic for the formation of structured galaxies. To fully grasp the significance of this, imagine stepping back in time, not just a few thousand years or a few million years but billions of years, back to when the universe was still in its infancy. The first few 100 million years after the Big Bang were marked by extreme heat and intense radiation. During this time, the universe was still in a state of chaos, with particles and light scattering freely through space. There were no stars, no galaxies, only a formless, primordial fog. It wasn't until hundreds of millions of years later that gravity began to pull matter together, slowly coalescing into the first stars and eventually galaxies. According to everything we thought we knew, galaxies should not have formed so soon after the Big Bang. They were supposed to have taken longer to materialize, as the universe gradually cooled and settled. But this galaxy didn't follow that pattern. It seemed to have formed rapidly in a time frame that shouldn't have been possible. The discovery suggested that the processes we've assumed were necessary for galaxy formation, processes involving gravity, cooling, and the accumulation of matter, might not have been as straightforward as we once thought. This galaxy was a clue, a tantalizing glimpse into a hidden chapter of the universe's history. It was as though the galaxy had arrived out of time, breaking free from the rules that governed its birth. This new frontier in galaxy formation opened up countless questions, all of them seemingly impossible to answer. How had this galaxy formed so early in the universe's history? What conditions could have allowed it to bypass the usual steps of galaxy evolution? And if this galaxy existed in a time when we thought galaxies were impossible, what other hidden anomalies could be lurking in the dark expanse of space, waiting to be discovered? As astronomers continued to study this galaxy, they began to piece together a more detailed picture of its properties. They observed its sheer size, which was much larger than expected for a galaxy so early in the universe's history. It was dense, compact, and unusually bright, traits that are typically associated with galaxies much older than it should have been. The galaxy seemed to have undergone rapid growth, collapsing under its own gravity to form a massive structure that shouldn't have been able to exist at that stage of cosmic history. The more they investigated, the more peculiarities emerged. For example, the galaxy's star formation rate was incredibly high, much faster than what was observed in more mature galaxies. While most galaxies take billions of years to reach their full potential, this one seemed to be rushing through its life cycle, skipping steps in its evolution. It was almost as if the galaxy was in a hurry to grow up, as though it was trying to defy the natural laws that govern cosmic evolution. At first, these observations were met with skepticism. It was hard to imagine that such an extraordinary galaxy could exist in a time when the universe was supposed to be a chaotic mess of particles and radiation. Astronomers were reluctant to embrace the idea that their models, years of research, observation, and calculation, could be wrong. But the more they examined the evidence, the more they realized that this galaxy could not be explained away as an anomaly or a fluke of data. This was something new. Something beyond what we thought was possible. The implications were staggering. If this galaxy had formed so quickly, then it suggested that the conditions for galaxy formation could have been different from what we previously understood. Maybe the universe was capable of creating galaxies in ways we hadn't yet imagined, ways that defy the predictable, gradual process that we had come to associate with cosmic evolution. It raised the possibility that our understanding of how the universe works is incomplete, that there are fundamental processes at play that we haven't yet uncovered. It wasn't just a matter of a single galaxy, though. The discovery of this galaxy forced astronomers to reconsider the entire framework of galaxy formation. If a galaxy could form under these unexpected conditions, then what else could be out there, hidden in the cosmic depths, waiting to be found? Was this galaxy a one-off, or did it represent a new class of galaxies, ones that had formed in a way that was completely different from anything we had seen before? And what did this mean for our understanding of the early universe? The discovery began to resonate on a broader scale, sparking a new wave of research into the early cosmos. If this galaxy was a fluke, it could be dismissed as an anomaly. But if it was part of a larger, untapped phenomenon, it could change the entire trajectory of cosmology. And so, astronomers set their sights on uncovering more galaxies like this one, hoping that by studying them, they could unlock secrets about the early universe, the nature of galaxy formation, and the very laws that govern the cosmos. With each new discovery, the mystery deepened. The more they learned, the more questions they uncovered. Was the galaxy's rapid formation the result of an unknown force or factor? Could it have been influenced by something outside of the ordinary processes of galaxy evolution? And if so, what did that mean for our understanding of the universe's origins? This galaxy, and the questions it raised, pushed astronomers into a new frontier of exploration, one that demanded a rethinking of established theories and opened up possibilities that had once seemed impossible. It was a turning point in our understanding of the universe, a discovery that reminded us of how little we truly know. The universe, as vast and complex as it is, continues to surprise us, revealing that even the most well-established truths are subject to change. As the team continued their work, they knew that the discovery of this galaxy was just the beginning. It was a stepping stone, a catalyst for a new era in astronomy. The frontier of galaxy formation had just expanded, and who knew what else lay beyond the horizon, waiting to be discovered? At the heart of every great scientific discovery lies a simple truth. The more we learn, the more we realize how much we don't know. For centuries, astronomers and physicists have looked up at the stars and attempted to make sense of the universe. From the first tentative glimpses of distant galaxies to the launch of sophisticated space telescopes, humanity has steadily expanded its understanding of the cosmos. Yet with every new piece of knowledge, we are confronted with the humbling reality that the universe is far more complex and mysterious than we ever imagined. The discovery of this galaxy, so far removed from the patterns that astronomers thought they understood, forces us to confront the limits of human knowledge. How much do we really know about the universe? And how much of what we think we know is merely a reflection of our current limitations, bound by the tools and theories we've developed so far. This galaxy, unlike any we've encountered before, seems to mock the very foundation of modern cosmology. And in doing so, it raises a profound question. Are we truly ready to understand the cosmos, or are we simply fooling ourselves? The search for knowledge is an ancient pursuit, one that has driven humanity to reach beyond the stars for millennia. From the earliest astronomers who charted the night sky with nothing more than the naked eye, to the pioneering scientists who developed telescopes and mathematical models to explain the universe's workings, our understanding has grown in leaps and bounds. Yet even as we push the boundaries of human knowledge, we continue to encounter mysteries that elude our grasp. Every discovery brings with it more questions, and with each new question the universe seems to reveal just how much we still don't know. In the case of this galaxy, we are forced to ask fundamental questions that challenge the very pillars of modern astronomy. How could a galaxy form so early in the universe's history, when the conditions we thought were necessary for galaxy formation didn't exist? What does it say about our current models of cosmic evolution that a galaxy like this one could emerge when we believed such a thing was impossible? The questions are dizzying, and the more we dig into the data, the more we realize that the answers may not lie within the realm of our current understanding. It's easy to forget, when we look at the stunning images of distant galaxies or the elegant equations that describe the cosmos, that science itself is a constantly evolving process. What we know today may not be the whole truth, and what we believe to be true may one day be discarded as outdated or incomplete. As new technologies emerge and new theories take shape, the lens through which we view the universe changes. Yet, for all our advancements, we are still bound by the limitations of our tools, our methods, and our imaginations. This galaxy, which has emerged seemingly out of nowhere, serves as a stark reminder of the limits of human knowledge. It is a reminder that no matter how advanced our instruments become, there will always be regions of the universe that remain beyond our reach. The discovery forces us to acknowledge that there may be aspects of the universe, its origin, its evolution, its very structure, that are simply beyond our comprehension. The reality is that there are limits to human understanding, and there may be phenomena that exist in the universe that are so far removed from our experience that we can never fully grasp them. The beauty of science, however, is that even in the face of these limits, the pursuit of knowledge continues. It's in our nature to question, to explore, and to seek answers even when those answers seem elusive. The galaxy we've discovered may defy our current understanding, but it also opens up new avenues for exploration. In the face of the unknown, scientists will continue to probe, hypothesize, and search for answers. They will continue to expand the boundaries of human knowledge, even if they may never fully understand everything. But as we push forward, we are also reminded of the importance of humility. There was a time not so long ago when the universe was thought to be static and unchanging, a vast, orderly expanse that revolved around the Earth. For centuries, humans believed that the Earth was the center of the universe and everything else revolved around it. It wasn't until the work of astronomers like Copernicus, Galileo, and Kepler that this idea was overturned. And even then, the true scale of the cosmos remained beyond comprehension. The discovery of this galaxy, this unexpected outlier, is a humbling reminder that the universe is much more complex than we can imagine. It reminds us that there is always more to learn, and that every discovery we make brings us one step closer to understanding the vast, unknowable reality we are part of. There is a certain beauty in the unknown, in the realization that we are not the ultimate arbiters of knowledge. The more we uncover, the more we realize how much remains hidden, how much is still out of reach. And perhaps that is the most profound lesson of all, that the universe is not something to be fully understood, but something to be explored, appreciated, and respected. It's a lesson in humility, a reminder that no matter how far we've come in our quest for knowledge, we will never have all the answers. This humility is not a sign of failure but of wisdom. True knowledge is not about having all the answers, it's about recognizing the vastness of what remains unknown. Every new discovery, every new piece of data, is an opportunity to expand our understanding, but it's also an invitation to embrace the mystery of existence. And in embracing that mystery, we become better equipped to approach the universe with the kind of wonder and awe that drives true scientific inquiry. In the case of this galaxy, the discovery forces us to confront the possibility that our current models and theories may not be as complete as we once thought. It challenges us to ask whether there is something deeper, something more fundamental, that we've overlooked in our understanding of the cosmos. Perhaps there are forces at work in the universe that we have yet to even imagine. And in asking these questions, we begin to uncover a new frontier of thought, one that requires us to move beyond the limits of our current knowledge and explore the unknown with open minds and a sense of wonder. As we look to the future, we realize that the discovery of this galaxy is not just a scientific breakthrough, it's a call to arms for a new generation of thinkers, explorers, and dreamers. The universe is vast, and its mysteries are endless. But as long as we continue to ask questions, to push the boundaries of our understanding, we move closer to unlocking the secrets of existence. And in that journey, we are reminded that the greatest discoveries often arise not from answers, but from the questions themselves. The limits of human knowledge are not something to fear, they are an invitation to explore, to seek, and to learn. As long as we remain open to the unknown, the universe will continue to surprise us. And in that mystery, we will find the answers to the most profound questions we've ever asked. To understand the significance of this groundbreaking discovery, we must first delve into the process by which galaxies are born and evolve over time. Galaxies are the fundamental building blocks of the universe, vast, sprawling collections of stars, gas, dust, and dark matter, bound together by the force of gravity. Yet, as we observe galaxies across the universe, we find that their origins are far more complex and mysterious than one might imagine. Understanding how galaxies form, grow, and change provides us with the necessary framework to comprehend why this new discovery is so astonishing. In the earliest moments after the Big Bang, the universe was an incredibly hot, dense soup of particles, constantly expanding and cooling. For the first few 100,000 years, the universe was opaque, filled with a mist of hydrogen and helium. It wasn't until around 380,000 years after the Big Bang that the universe cooled enough for atoms to form, allowing light to travel freely. This moment, known as the recombination, marked the birth of the cosmic microwave background radiation, a faint glow that still echoes throughout the universe, providing us with a snapshot of the early cosmos. At this stage, the universe was still far from the rich, structured landscape of galaxies that we see today. It was a chaotic and formless expanse, devoid of stars, planets, and galaxies. But slowly, as the universe expanded and cooled, the first seeds of structure began to form. Gravity, the fundamental force that governs the movement of all matter, began to pull together clumps of hydrogen gas. These clumps, known as dark matter halos, acted like the scaffolding of the universe, creating pockets where matter could begin to accumulate. The first stars, massive, luminous, and short-lived, emerged from these dense regions of gas. They ignited in violent explosions, filling the young universe with light and energy. These early stars were the birth pangs of galaxies, and over time they began to group together into clusters. It was in these dense clusters of stars that galaxies began to take shape. The process of galaxy formation is slow and gradual. Stars form in massive clouds of gas, and over millions of years, these stars come together, creating the galaxy structure. As the stars continue to form, they create a gravitational pull that shapes the galaxy, pulling gas and dust together and forcing them to condense into new stars. This process is known as hierarchical merging. It suggests that galaxies grow by merging with other smaller galaxies, constantly accumulating more stars and gas along the way. As galaxies collide and merge, their shapes evolve, and new stars are born from the remnants of the collisions. The interaction between galaxies, whether it's the merging of two small galaxies or the slow dance of a galaxy interacting with its neighbor, helps to drive the growth and evolution of galaxies over time. In this process, some galaxies grow rapidly while others evolve more slowly. It's a cosmic dance, shaped by the forces of gravity and the interactions between different components of the galaxy. For billions of years, galaxies followed this pattern of growth and evolution. Some galaxies grew large and spiral-shaped, like the Milky Way, while others remained small, irregular, and chaotic. Galaxies would continue to collide and merge, their stars moving in unpredictable orbits, and yet the overall structure of the galaxy remained intact. The stars within a galaxy orbit its center, while gas and dust form nebulae, giant clouds of gas and dust where new stars are born. This ongoing cycle of star birth and death shapes the galaxy over time, influencing its size, shape, and composition. Now, this is where the story of our newly discovered galaxy takes a dramatic turn. The conventional model of galaxy formation tells us that the first galaxy should have emerged only hundreds of millions of years after the Big Bang, once the universe had cooled enough for the necessary conditions to form stars and gas clouds. These early galaxies were thought to be small and primitive, just beginning to coalesce into the massive organized structures we see today. However, the galaxy discovered in this story doesn't fit that narrative. It defies the conventional understanding of how and when galaxies should form, and it challenges the very foundations of galaxy formation. This galaxy, as the astronomers observed, seemed to have formed much earlier than expected, at a time when the universe was still in its infancy. According to the established timeline, galaxies should have formed after the first few 100 million years of the universe's existence. Yet this galaxy appears to have formed much sooner, at a time when the universe was still filled with chaos and energy. How could it have formed so early? What factors allowed it to defy the traditional model of galaxy formation? The answer is still unclear, but what is certain is that this discovery has opened up a new frontier in our understanding of how galaxies come into existence. If galaxies can form so quickly, it raises a number of intriguing possibilities. Could the early universe have had conditions that allowed galaxies to form at a faster rate than previously thought? Perhaps there were factors at play that we've overlooked. Unseen forces or conditions that allowed for the rapid formation of galaxies, even when the universe was still very young. In this discovery, we are faced with the possibility that there may be more than one way for galaxies to form, each shaped by the unique conditions of the universe at the time. It suggests that there could be unknown factors driving galaxy formation, factors that are yet to be fully understood. For example, the presence of dark matter, the invisible substance that makes up a large portion of the universe's mass, could be influencing galaxy formation in ways we don't fully comprehend. The discovery could also mean that the early universe had a different set of conditions, perhaps a denser environment with more gas and dust available for star formation, that enabled galaxies to form more rapidly than we've believed. What makes this discovery even more fascinating is that it forces us to rethink not just the timeline of galaxy formation, but the very nature of the early universe. Could the rapid formation of this galaxy be indicative of a larger, unexplored pattern of cosmic evolution? Could there be a whole class of galaxies out there, waiting to be discovered, that formed in ways we never imagined? If this galaxy is part of a broader phenomenon, it could be the key to unlocking new theories of cosmology and galaxy formation, pushing us to reconsider our most fundamental assumptions about the universe. For astronomers and cosmologists, the implications of this discovery are enormous. It suggests that the universe may have been far more complex and dynamic in its early stages than we thought. And as scientists continue to analyze this galaxy and others like it, they are likely to uncover even more mysteries, new forces, new mechanisms, and new processes that could change the way we think about the birth of galaxies and the evolution of the cosmos. The discovery is a reminder that science is a constantly evolving journey, one that is full of surprises, and one that may very well rewrite the story of the universe itself. This galaxy, in all its mystery and complexity, serves as a reminder that the story of the universe is far from complete. Every discovery we make brings us one step closer to understanding the vast, intricate forces that shape the cosmos, but it also reveals just how much we still have to learn. The universe is a constantly unfolding puzzle, and each new piece we uncover brings more questions, more possibilities, and more wonder. The discovery of this galaxy is not just a milestone in the history of astronomy, it is a new chapter in the ongoing story of the universe, a story that is still being written. To fully appreciate the significance of this new galaxy and the radical questions it raises, we must first examine the intricate structure of a galaxy. Galaxies, in all their splendor, are not just vast collections of stars strewn across space. They are dynamic, complex systems, each composed of multiple components that interact with one another in ways that govern their evolution. From their massive central cores to their sprawling arms, the anatomy of a galaxy is both fascinating and enigmatic. Understanding this structure helps us appreciate why this new discovery is so extraordinary, because it challenges the established patterns of galaxy formation that we have long relied upon. At the core of every galaxy lies its most mysterious and powerful feature, the central black hole. For years, scientists have observed the effects of these invisible, supermassive objects at the heart of many galaxies. These black holes, which can be millions or even billions of times more massive than our Sun, are often surrounded by a disk of gas and dust, spiraling inward as it falls toward the event horizon, the point of no return. The gravitational pull of a supermassive black hole is so intense that it influences the entire galaxy. The energy released as matter falls into the black hole creates a dazzling display of light, known as an active galactic nucleus, AGN. These AGNs are among the brightest objects in the universe, their radiation detectable even from billions of light-years away. Around the black hole lies the galactic bulge, a dense cluster of stars and other matter. This region is often more spherical in shape, contrasting with the flat, disc-like structure of the rest of the galaxy. It is home to the oldest stars in the galaxy, massive, red giants that have been slowly evolving for billions of years. The stars in the bulge orbit the center of the galaxy in elliptical paths, their motions influenced by the gravitational pull of the central black hole. The disk of the galaxy, which is the most recognizable part, is where the majority of a galaxy's stars reside. This flat, spiral-shaped region contains billions of stars, interstellar gas, and dust. In a spiral galaxy like the Milky Way, the disk is divided into spiral arms, which are regions where the gas and dust are denser, leading to higher rates of star formation. These spiral arms, which wind outward from the galactic center, are where we see the birth of new stars and nebulae, vast clouds of gas and dust that collapse under their own gravity to form new young stars. These star-forming regions, known as stellar nurseries, are among the most beautiful and awe-inspiring sights in the universe, glowing brightly with the light of newborn stars. The outer regions of the galaxy, often referred to as the galactic halo, are less populated but no less important. The halo is composed of older stars as well as dark matter, which is an invisible substance that makes up the majority of a galaxy's mass. Dark matter doesn't emit light or energy, making it impossible to detect directly, but its presence can be inferred by the gravitational effects it has on visible matter. The halo extends far beyond the visible disk of the galaxy, and it plays a crucial role in the overall structure of the galaxy, influencing its shape and rotation. A galaxy's spiral arms, star-forming regions, and central bulge are in constant motion, with each part of the galaxy influenced by the gravitational pull of other components. Stars orbit the galactic center in elliptical paths, with their speed depending on their distance from the center. This motion creates a dynamic, ever-evolving system. As stars form, age, and die, they release heavy elements into the surrounding space, enriching the interstellar medium and contributing to the next generation of stars. The gas in the galaxy is constantly cycling through different phases, from cold, dense clouds of molecular gas where stars are born, to hotter, more diffuse gas that is heated by the radiation of young stars and supernova explosions. This ongoing cycle of star birth, death, and gas recycling gives a galaxy its character and drives its evolution. In addition to the visible matter, galaxies are also influenced by the invisible force of dark matter. Dark matter, which makes up around 85% of a galaxy's mass, is not well understood, but its gravitational effects are undeniable. It doesn't interact with light or other forms of electromagnetic radiation, so it cannot be seen directly. However, scientists have inferred its existence through the way galaxies behave. For example, the rotation curves of galaxies, how the speed of stars in a galaxy changes with distance from the center, cannot be explained by the amount of visible matter alone. The presence of dark matter is what allows the outer regions of galaxies to rotate at the observed speeds without flying apart. Now, as we zoom out and begin to think about the discovery of this new galaxy, we must ask, what sets this galaxy apart from others we have observed? What is it about its anatomy that challenges everything we thought we knew about galaxy formation? To understand this, we need to consider the unique features that define this galaxy, the properties that make it stand out in the context of our existing knowledge of cosmology. For one, this galaxy appears to have formed much earlier in the universe's history than expected. The standard model of galaxy formation suggests that galaxies begin as small clumps of gas and dust, which gradually merge and grow over billions of years. However, this galaxy seems to have emerged during a time when conditions were not ideal for galaxy formation. The universe, at that point, was still in its early stages, filled with radiation and high-energy particles. The ingredients for galaxy formation, which include cold gas and dust, were sparse. How could this galaxy have formed so quickly, given the chaotic conditions of the early universe? Moreover, this galaxy appears to be much larger and more developed than its counterparts from the same time period. Galaxies that formed early in the universe were thought to be small, irregular in shape, and far less structured than galaxies we see today. However, this galaxy seems to have defied those expectations, displaying a well-defined structure and a degree of organization that challenges conventional theories of cosmic evolution. Its size and brightness suggest that it has been able to form stars at an unusually rapid rate, a phenomenon that would have been difficult to achieve in the early universe, when resources like gas and dust were less abundant and star formation was expected to be slower. Even more striking is the fact that this galaxy doesn't fit the expected timeline for galaxy evolution. Based on what we know, galaxies should have formed gradually, with smaller ones merging over time to create larger structures. Yet this galaxy seems to have formed much faster than that model would suggest. Its structure, its composition, and its location in the universe all point to a level of complexity that shouldn't have existed so soon after the Big Bang. The discovery of this galaxy forces us to ask new questions about the anatomy of galaxies themselves. What role did dark matter play in its formation? Could the early universe have had conditions that we haven't yet considered, conditions that allowed galaxies to form in ways we didn't think were possible? What does the rapid formation of stars in this galaxy tell us about the state of the universe at the time? And how does this galaxy fit into the larger framework of cosmic evolution? These are the questions that scientists are now grappling with as they study this extraordinary discovery. In examining the anatomy of galaxies, we find that they are not just static objects but dynamic, ever-changing systems. The discovery of this galaxy challenges everything we thought we knew about the evolution of these systems, urging us to rethink the very processes that shape them. This galaxy, with its unique structure, rapid growth, and early formation, offers a tantalizing glimpse into the complexities of the universe, a universe that is still revealing its secrets, one discovery at a time. The discovery of this extraordinary galaxy raises profound questions not only about its formation but also about the broader processes of cosmic evolution. It forces us to rethink the entire timeline of the universe's history, challenging the models and assumptions we've long held about how galaxies form, evolve, and interact with one another. For decades, scientists have worked within the framework of the Cosmic Standard Model, a well-established theory that outlines how galaxies should develop, grow, and change over billions of years. But this galaxy doesn't fit into that model. In fact, it appears to have violated some of the very principles we've used to understand the evolution of the cosmos. To fully comprehend the significance of this anomaly, we must first look at what we know about cosmic evolution. According to current theories, after the Big Bang, the universe was initially a hot, dense soup of particles. It wasn't until hundreds of thousands of years later, when the universe had cooled enough, that atoms began to form. This period marked the start of cosmic evolution as we know it. In the early stages of the universe, the first stars and galaxies began to form, gradually coalescing from vast clouds of gas and dust. Over the next billions of years, galaxies would grow, collide, and merge, shaping the complex and diverse structures that we see in the universe today. However, one of the key assumptions of this model is that galaxies form slowly. Over time, gravity causes smaller clumps of gas and dark matter to collide and merge, creating larger and more complex galaxies. This process is gradual and takes place over vast stretches of time, billions of years. The Standard Model suggests that galaxies formed gradually, starting from small, irregular blobs of gas, which later organized into the more structured forms we observe today, like spiral galaxies or elliptical galaxies. The slow pace of this process is a fundamental part of our understanding of how the universe evolved. Now, imagine the shock and awe of astronomers when they realized that this new galaxy didn't fit this timeline. It appears to have formed much earlier than expected, in an era of the universe that was still in its infancy. The universe, at this point, was full of radiation, and conditions were chaotic, not conducive to galaxy formation. Gas and dust were scattered and sparse. Yet, against all odds, this galaxy had somehow managed to form during a time when it was thought that the ingredients for galaxy creation, cold, dense gas, simply didn't exist. This challenges the entire premise of how galaxies are supposed to form and evolve. This anomaly forces us to ask some fundamental questions. How could such a galaxy form so early? What conditions allowed it to bypass the gradual process of galaxy formation that we've always assumed was the only way for galaxies to come into existence? Could there have been factors in the early universe that we haven't yet considered? Factors that accelerated the process of galaxy formation? Could this galaxy represent a new chapter in the story of cosmic evolution, one that we never saw coming? The discovery of this galaxy isn't just a curiosity, it's a game changer. It forces astronomers to reconsider the basic tenets of cosmic evolution and galaxy formation. It suggests that there may be unknown mechanisms at work in the universe that we haven't yet identified, forces that allowed galaxies to form in ways we never imagined. What's even more perplexing is that this galaxy doesn't just form early, it also appears to be much more developed and structured than it should be for its age. In the early universe, galaxies were believed to be small, irregular, and lacking the complexity of more mature galaxies. But this galaxy seems to defy those expectations, suggesting that there may be processes at work that accelerated the formation and organization of galaxies. As scientists study this anomaly, they are being forced to re-examine the entire history of cosmic evolution. If this galaxy formed rapidly, it could imply that there are aspects of the universe's early conditions that we haven't yet understood. Could the early universe have had more gas, more dust, or different conditions than we originally thought? Could there have been influences, possibly from dark matter or some other unseen force, that allowed for the faster formation of galaxies? These questions represent a major shift in our understanding of the universe. The standard model of galaxy formation, which suggests a gradual process over billions of years, no longer seems to hold up in the face of this discovery. Instead, it raises the possibility that galaxies may not have followed the slow, steady progression that we once believed. Perhaps there are multiple pathways for galaxy formation, some of which occur much more quickly than we ever imagined. This revelation is particularly exciting because it opens up new areas of research. Scientists can now explore the conditions that allowed for the rapid formation of this galaxy, and potentially discover new mechanisms that govern the evolution of galaxies in the early universe. It could also lead to the discovery of more galaxies that defy the traditional timeline, revealing a completely new class of galaxies that have formed in ways we didn't know were possible. The implications of this discovery stretch far beyond just this single galaxy. It forces us to reconsider not just the process of galaxy formation but the larger picture of cosmic evolution. The timeline of the universe's history, which has long been based on the assumption that galaxies form slowly and steadily over time, may need to be rewritten. If this galaxy formed much earlier than expected, it suggests that the conditions of the early universe were more complex and varied than we currently understand. This could have profound implications for our understanding of the Big Bang itself. Did the universe go through phases of rapid growth and evolution, periods when galaxies could have formed more quickly than we thought? Could there have been periods of cosmic acceleration that allowed for the faster development of complex structures like galaxies? These are questions that may take years, if not decades, to fully answer. But the discovery of this galaxy has opened the door to a new era of research, one where scientists will explore new theories and models of cosmic evolution. What makes this discovery even more tantalizing is that it suggests the universe may still hold many secrets, mysteries that we have yet to uncover. If galaxies could form so rapidly and so early, what else might be hidden out there in the cosmos? Could there be other anomalies, other unexpected galaxies waiting to be discovered? This discovery is a reminder that the universe is full of surprises, and that our understanding of it is still in its infancy. We've come a long way in our quest to understand the cosmos, but as this galaxy shows, we still have much to learn. Ultimately, this galaxy represents more than just an isolated anomaly, it's a key to unlocking the deeper mysteries of cosmic evolution. It challenges us to think differently about the universe and about the processes that have shaped it. In uncovering its secrets, we will gain a new understanding of the forces that govern the universe and the ways in which galaxies, stars, and even entire galaxies can form and evolve. The discovery of this galaxy is just the beginning of what promises to be an exciting and transformative journey into the unknown. And as we continue to explore the universe, we may find that the answers to some of our biggest questions are just waiting to be uncovered. As we attempt to unravel the mysteries surrounding this newly discovered galaxy, we are inevitably led to confront the enigmatic force that shapes much of the universe yet remains unseen: dark matter. This invisible substance, which makes up roughly 85% of the total mass in the universe, has become one of the most profound puzzles in modern science. Despite its overwhelming influence on the cosmos, we know very little about dark matter. Its presence is only detectable through its gravitational effects on visible matter, such as stars and galaxies. So why does it matter in the context of this extraordinary galaxy? First, let's step back and understand the essential role dark matter plays in the formation and structure of galaxies. In the standard model of cosmology, galaxies are thought to form from large clouds of gas and dust that are drawn together by the gravitational pull of dark matter. This invisible substance provides the scaffolding around which visible matter, stars, gas, dust, can accumulate. Without dark matter, galaxies would not have the gravitational foundation needed to hold their structure together. In fact, most galaxies, including our own Milky Way, would likely have been torn apart by the forces of gravity, unable to maintain their spiral shapes or hold their stars in place. The discovery of this unusual galaxy forces us to reconsider what we thought we knew about dark matter's role in galaxy formation. While dark matter has long been assumed to play a fundamental part in shaping galaxies, the nature of its influence remains shrouded in mystery. One thing we do know is that galaxies, particularly those that formed early in the universe's history, are thought to have been influenced heavily by the gravitational pull of dark matter. The dark matter halos that surround galaxies help to anchor their growth, ensuring that the galaxies do not dissolve into the void. These halos act as a cosmic glue, providing the necessary mass to attract gas and dust and, eventually, form stars. Now, considering the rapid formation of this galaxy, we have to ask, Could dark matter have played a role in the galaxy's unusually swift development? The conventional theory is that galaxies form gradually, starting from small clumps of gas and dust that come together under the influence of gravity. However, this galaxy's early formation raises questions about how dark matter might have affected its evolution. Could the presence of dark matter in this region of space have acted as a catalyst, accelerating the galaxy's formation and giving it the structure and mass we observe today? Dark matter is theorized to be distributed in large halos surrounding galaxies, and the density of this dark matter could vary across different regions of the universe. If this newly discovered galaxy is located in an area with an unusually high concentration of dark matter, it might explain why it was able to form so quickly. The gravitational pull of the dark matter could have drawn in gas and dust at an accelerated rate, fostering faster star formation and leading to a more mature structure than we would expect from a galaxy of its age. This would suggest that dark matter's role in galaxy formation is more complex than previously thought, perhaps influencing not only the overall shape of a galaxy but also the speed at which it forms. One of the intriguing possibilities is that the early universe may have had regions of higher dark matter density, creating conditions that allowed for the faster aggregation of matter and the rapid formation of galaxies. These regions might have acted as cosmic hotbeds for galaxy creation, with the dense concentration of dark matter providing the necessary gravitational pull to draw together the cold gas and dust needed to form stars. If this hypothesis holds true, it could change our understanding of how galaxies formed during the first few 100 million years after the Big Bang. However, there are also deeper mysteries surrounding the nature of dark matter itself. While scientists are confident that dark matter exists, its exact composition remains unknown. Some theories suggest that dark matter is made up of yet undiscovered particles that interact very weakly with normal matter, making them nearly impossible to detect directly. Others propose that dark matter could be composed of primordial black holes or other exotic objects. Whatever its true nature may be, its role in shaping the universe is undeniable. From the formation of galaxies to the large-scale structure of the cosmos, dark matter serves as the invisible hand that guides the universe's evolution. The discovery of this galaxy and the questions it raises about the speed and nature of its formation compels scientists to investigate whether dark matter could be influencing galaxy formation in ways we have yet to fully understand. Could there be variations in dark matter density across the universe that might explain the rapid formation of this galaxy? Could dark matter be facilitating faster gravitational collapse, allowing galaxies to form at an accelerated pace, bypassing the gradual process we have always assumed? If so, this would suggest that our current models of dark matter and galaxy formation may be incomplete, requiring a major revision in how we think about the evolution of the cosmos. Interestingly, some researchers have proposed that dark matter could be interacting with normal matter in ways we don't yet understand. While dark matter has long been thought to be passive, interacting only through gravity, new theories suggest that it could have other, unknown interactions with visible matter, perhaps in the form of weakly interacting particles or new forces. If dark matter is more dynamic than we currently understand, it could play a much more active role in the formation and evolution of galaxies, including this one. This would mean that galaxies could form under the influence of dark matter in ways that go beyond mere gravitational attraction. Moreover, the discovery of this galaxy presents a unique opportunity to study dark matter in action. By examining the way this galaxy formed and evolved, scientists may be able to gain new insights into the distribution of dark matter and its interaction with visible matter. If the galaxy's rapid formation is tied to dark matter, its study could shed light on the elusive properties of this mysterious substance. Scientists could observe how dark matter affects star formation, galaxy size, and the overall structure of the galaxy, providing critical data that could help to refine our understanding of dark matter's role in the universe. The more we learn about dark matter, the more we realize just how little we know. Despite its dominant presence in the universe, dark matter remains one of the greatest mysteries in science. It doesn't emit light, absorb it, or reflect it, making it virtually impossible to detect directly. And yet, its effects are evident in the way galaxies move and in the overall structure of the universe. From the motions of galaxies to the cosmic web that stretches across the universe, dark matter is the unseen architect behind the cosmos. As we attempt to understand the true nature of this galaxy, we must also come to terms with the fact that dark matter may hold the key to unlocking some of the deepest mysteries of the universe. Whether it is influencing the rapid formation of galaxies or shaping the very fabric of space itself, dark matter's impact on cosmic evolution cannot be overstated. The discovery of this galaxy, and the questions it raises about the formation of galaxies in the early universe, is not just an opportunity to study one object. It is a chance to delve deeper into the unknown world of dark matter and the profound role it plays in shaping the cosmos. Through continued research, we may one day unlock the secrets of dark matter, bringing us one step closer to understanding the true nature of the universe. As we attempt to unravel the mysteries surrounding this newly discovered galaxy, we are inevitably led to confront the enigmatic force that shapes much of the universe yet remains unseen: dark matter. This invisible substance, which makes up roughly 85% of the total mass in the universe, has become one of the most profound puzzles in modern science. Despite its overwhelming influence on the cosmos, we know very little about dark matter. Its presence is only detectable through its gravitational effects on visible matter, such as stars and galaxies. So why does it matter in the context of this extraordinary galaxy? First, let's step back and understand the essential role dark matter plays in the formation and structure of galaxies. In the standard model of cosmology, galaxies are thought to form from large clouds of gas and dust that are drawn together by the gravitational pull of dark matter. This invisible substance provides the scaffolding around which visible matter, stars, gas, dust, can accumulate. Without dark matter, galaxies would not have the gravitational foundation needed to hold their structure together. In fact, most galaxies, including our own Milky Way, would likely have been torn apart by the forces of gravity, unable to maintain their spiral shapes or hold their stars in place. The discovery of this unusual galaxy forces us to reconsider what we thought we knew about dark matter's role in galaxy formation. While dark matter has long been assumed to play a fundamental part in shaping galaxies, the nature of its influence remains shrouded in mystery. One thing we do know is that galaxies, particularly those that formed early in the universe's history, are thought to have been influenced heavily by the gravitational pull of dark matter. The dark matter halos that surround galaxies help to anchor their growth, ensuring that the galaxies do not dissolve into the void. These halos act as a cosmic glue, providing the necessary mass to attract gas and dust and, eventually, form stars. Now, considering the rapid formation of this galaxy, we have to ask, could dark matter have played a role in the galaxy's unusually swift development? The conventional theory is that galaxies form gradually, starting from small clumps of gas and dust that come together under the influence of gravity. However, this galaxy's early formation raises questions about how dark matter might have affected its evolution. Could the presence of dark matter in this region of space have acted as a catalyst, accelerating the galaxy's formation and giving it the structure and mass we observe today? Dark matter is theorized to be distributed in large halos surrounding galaxies, and the density of this dark matter could vary across different regions of the universe. If this newly discovered galaxy is located in an area with an unusually high concentration of dark matter, it might explain why it was able to form so quickly. The gravitational pull of the dark matter could have drawn in gas and dust at an accelerated rate, fostering faster star formation and leading to a more mature structure than we would expect from a galaxy of its age. This would suggest that dark matter's role in galaxy formation is more complex than previously thought, perhaps influencing not only the overall shape of a galaxy but also the speed at which it forms. One of the intriguing possibilities is that the early universe may have had regions of higher dark matter density, creating conditions that allowed for the faster aggregation of matter and the rapid formation of galaxies. These regions might have acted as cosmic hotbeds for galaxy creation, with a dense concentration of dark matter providing the necessary gravitational pull to draw together the cold gas and dust needed to form stars. If this hypothesis holds true, it could change our understanding of how galaxies formed during the first few 100 million years after the Big Bang. However, there are also deeper mysteries surrounding the nature of dark matter itself. While scientists are confident that dark matter exists, its exact composition remains unknown. Some theories suggest that dark matter is made up of yet undiscovered particles that interact very weakly with normal matter, making them nearly impossible to detect directly. Others propose that dark matter could be composed of primordial black holes or other exotic objects. Whatever its true nature may be, its role in shaping the universe is undeniable. From the formation of galaxies to the large-scale structure of the cosmos, dark matter serves as the invisible hand that guides the universe's evolution. The discovery of this galaxy and the questions it raises about the speed and nature of its formation compels scientists to investigate whether dark matter could be influencing galaxy formation in ways we have yet to fully understand. Could there be variations in dark matter density across the universe that might explain the rapid formation of this galaxy? Could dark matter be facilitating faster gravitational collapse, allowing galaxies to form at an accelerated pace, bypassing the gradual process we have always assumed? If so, this would suggest that our current models of dark matter and galaxy formation may be incomplete, requiring a major revision in how we think about the evolution of the cosmos. Interestingly, some researchers have proposed that dark matter could be interacting with normal matter in ways we don't yet understand. While dark matter has long been thought to be passive, interacting only through gravity, new theories suggest that it could have other, unknown interactions with visible matter, perhaps in the form of weakly interacting particles or new forces. If dark matter is more dynamic than we currently understand, it could play a much more active role in the formation and evolution of galaxies, including this one. This would mean that galaxies could form under the influence of dark matter in ways that go beyond mere gravitational attraction. Moreover, the discovery of this galaxy presents a unique opportunity to study dark matter in action. By examining the way this galaxy formed and evolved, scientists may be able to gain new insights into the distribution of dark matter and its interaction with visible matter. If the galaxy's rapid formation is tied to dark matter, its study could shed light on the elusive properties of this mysterious substance. Scientists could observe how dark matter affects star formation, galaxy size, and the overall structure of the galaxy, providing critical data that could help to refine our understanding of dark matter's role in the universe. The more we learn about dark matter, the more we realize just how little we know. Despite its dominant presence in the universe, dark matter remains one of the greatest mysteries in science. It doesn't emit light, absorb it, or reflect it, making it virtually impossible to detect directly. And yet, its effects are evident in the way galaxies move and in the overall structure of the universe. From the motions of galaxies to the cosmic web that stretches across the universe, dark matter is the unseen architect behind the cosmos. As we attempt to understand the true nature of this galaxy, we must also come to terms with the fact that dark matter may hold the key to unlocking some of the deepest mysteries of the universe. Whether it is influencing the rapid formation of galaxies or shaping the very fabric of space itself, dark matter's impact on cosmic evolution cannot be overstated. The discovery of this galaxy, and the questions it raises about the formation of galaxies in the early universe, is not just an opportunity to study one object. It is a chance to delve deeper into the unknown world of dark matter and the profound role it plays in shaping the cosmos. Through continued research, we may one day unlock the secrets of dark matter, bringing us one step closer to understanding the true nature of the universe. At the heart of the early universe's transformation lies one of the most fundamental and awe-inspiring events in cosmic history: the emergence of the first stars. These primordial beacons of light were the first to ignite after the Big Bang, marking the dawn of an era that would forever change the structure of the cosmos. The formation of the first stars, known as population 3 stars, is a pivotal moment in the history of the universe, as it set the stage for the creation of galaxies, heavy elements, and, ultimately, the complex structures we see today. To fully understand the significance of the galaxy discovered in this story, we must explore the origins of these first stars, their unique characteristics, and how their birth influenced the evolution of the universe. In the earliest moments after the Big Bang, the universe was a hot, dense, and largely featureless expanse of gas composed primarily of hydrogen and helium. This period, known as the Cosmic Dark Ages, was marked by a lack of stars, galaxies, or any other visible structures. The universe was filled with diffuse gas, and the light that was produced during the Big Bang, known as the cosmic microwave background radiation, was the only source of illumination. For hundreds of millions of years, the universe was a cold, dark, and empty space, with no way for us to see what lay beyond. However, the first stirrings of light began to appear around 200 to 400 million years after the Big Bang, as the universe began to cool and matter began to clump together under the influence of gravity. This clumping of gas, particularly hydrogen, marked the first steps toward the formation of the first stars. Over time, gravity caused small pockets of gas to collapse and condense, forming dense clouds that eventually became the birthplaces of the first stellar objects. These stars, known as population 3 stars, were unlike anything we observe today. Unlike the stars that form in the present-day universe, which are made up of a mixture of hydrogen, helium, and heavier elements, population 3 stars were composed almost entirely of hydrogen and helium. These stars were born from the simplest and most primordial ingredients, gas that had never been enriched by the heavy elements created by previous generations of stars. The unique composition of population 3 stars had profound implications for their formation, structure, and evolution. These stars were much more massive than the stars we are familiar with today. Lacking the heavy elements like carbon, oxygen, and nitrogen that make up the atoms of Earth and all living things, these stars were able to burn much hotter and more intensely. The high temperatures inside these stars created the conditions necessary for fusion reactions to occur at an accelerated rate, allowing these stars to grow to sizes far larger than any star in our galaxy today. These stars were colossal, often hundreds of times the mass of our Sun, and they burned through their fuel in a fraction of the time it takes modern stars to do so. Their lifetimes were short, on the order of a few million years, much faster than the billions of years of life that stars like the Sun enjoy. When these massive stars finally exhausted their fuel, they exploded in supernovae of unprecedented scale, releasing enormous amounts of energy and creating the heavy elements that would eventually go on to form the building blocks of planets and life. These first-generation stars were responsible for polluting the universe with the first heavy elements like carbon, oxygen, and iron, that would later become the foundation for life and all the structures we observe in the universe. In this way, the death of these stars played a crucial role in the cosmic evolution of matter, enabling the formation of more complex structures, including galaxies, stars, and planets. The formation of these stars was not an instantaneous event. It was the result of gradual processes that took place over millions of years. The first stars formed in regions of the universe where gas had begun to collapse under the influence of gravity. These early gas clouds were massive, containing thousands of times more mass than the gas clouds that form stars today. As the gas collapsed, it heated up, eventually reaching temperatures high enough for nuclear fusion to begin, and the first stars ignited. These stars were so massive that they became the centers of their own mini-galaxies, with smaller stars and gas clouds orbiting around them. The role of these early stars in shaping the universe cannot be overstated. They were the engines that ignited the formation of galaxies, the building blocks of all the cosmic structures that came later. They were also the creators of the elements necessary for life. As these stars exploded in supernovae, they spread their heavy elements throughout the universe, enriching the interstellar medium and allowing for the formation of subsequent generations of stars, planets, and eventually life itself. In a sense, the death of these stars marked the birth of the universe as we know it today, a universe filled with complex structures, life, and the possibility of discovery. Now, how does this all tie into the discovery of the extraordinary galaxy? This galaxy, which has emerged from the depths of cosmic history, likely owes its existence to these very first stars. If this galaxy formed during the era of the first stars, at the dawn of the reionization epoch, it would have been one of the many galaxies born from the ashes of population 3 stars. The high-energy radiation emitted by these stars, along with their subsequent explosions, would have triggered the formation of the gas clouds and structures that would eventually coalesce into galaxies like the one we are discovering. What makes this discovery particularly fascinating is the rapid formation of this galaxy. While we might expect that galaxies formed in the aftermath of these early stars should have taken billions of years to evolve into the large, well-structured galaxies we see today, this galaxy seems to have formed much more quickly. Could it be that the intense radiation from the first stars acted as a catalyst, triggering faster star formation and galaxy formation? Could the presence of these massive, short-lived stars have accelerated the process of galaxy assembly, allowing the galaxy to take shape far earlier than we had imagined? This galaxy's rapid formation challenges our traditional understanding of how galaxies develop over time. It suggests that the conditions of the early universe, shaped by the first stars and their explosive deaths, may have been far more conducive to the quick formation of complex structures than we previously believed. The study of this galaxy could provide valuable insights into the role of the first stars in galaxy formation, helping us to better understand the processes that led to the creation of the first cosmic structures. In examining the birth of the first stars, we are also forced to confront some of the largest unanswered questions in cosmology. How exactly did the first stars form? What factors influenced their size, their luminosity, and their lifespan? Could there have been more than one type of first star, each with different properties and influences on the universe? The study of these stars is still in its infancy, and discoveries like this galaxy challenge us to reconsider our models of stellar evolution and galaxy formation during the universe's earliest epochs. Ultimately, the emergence of the first stars is a key chapter in the larger story of the universe's evolution. They were the first sparks of light in an otherwise dark and lifeless universe, setting the stage for everything that followed. From these early stars came galaxies, elements, and the very conditions that made life possible. As we look at the newly discovered galaxy and reflect on its rapid formation, we are reminded that the universe is still full of surprises that continue to reshape our understanding of how the cosmos came to be and how it continues to evolve. Through these discoveries, we continue to witness the unfolding story of creation, from the first stars to the galaxies and beyond, revealing a deeper and more intricate narrative of cosmic evolution than we ever imagined. In the aftermath of the first stars and galaxies, the universe began to evolve from a chaotic soup of hydrogen and helium into a more structured, intricate cosmos. The birth of complex structures, galaxies, star clusters, and eventually, the superclusters and cosmic filaments we see today, marked a critical phase in cosmic evolution. These early structures provided the scaffolding for all the future complexity that would emerge, from stars forming in clusters to massive galaxy mergers that reshaped the very fabric of the universe. The discovery of this new galaxy, with its unexpected formation and rapid growth, offers a glimpse into the mechanics of this process, revealing how galaxies and other large-scale cosmic structures were born from the initial chaos of the universe's early years. At the heart of this transformation was gravity, the fundamental force that began to sculpt the universe's structure by pulling matter together. In the earliest stages of the universe, matter was distributed relatively evenly. But as the universe expanded and cooled, slight irregularities in the density of matter became the seed for larger structures. These density fluctuations created regions of greater mass, where gravity would slowly begin to pull matter inward. Over time, these regions grew, becoming the dark matter halos that are thought to surround every galaxy. The process by which these regions of matter collapsed to form the first galaxies was slow and methodical. Yet, it was also turbulent, as the gas within these early structures was subject to extreme temperatures and pressures, leading to star formation, violent stellar winds, and the eventual release of heavy elements into space. The birth of galaxies from these collapsing gas clouds is one of the most awe-inspiring phenomena in the universe. While it is difficult to fully understand the intricacies of this process, modern simulations of galaxy formation offer us a glimpse into how it might have unfolded. Initially, small clumps of gas, mostly hydrogen and helium, formed due to gravitational attraction. As these clumps collapsed inward, they heated up, eventually reaching temperatures high enough for nuclear fusion to begin. This led to the formation of the first stars, which provided the necessary light and heat to further shape the surrounding gas. These stars were not isolated. They formed in groups known as star clusters. These clusters were the building blocks of galaxies, and the earliest galaxies likely consisted of only a few stars clustered together in a relatively small, irregular structure. As these stars aged and died, they released heavy elements into the surrounding space through supernova explosions. These explosions enriched the gas around them, allowing for the formation of new, more complex stars. Over time, these stars began to form larger structures, eventually leading to the galaxies we observe today. The structure of early galaxies was vastly different from the more well-defined spirals or ellipticals that populate the universe today. Instead, they were small, irregular, and often chaotic. It wasn't until later, as galaxies began to merge and interact with one another, that they began to acquire more defined shapes and sizes. This process of galactic assembly was fundamental to the growth of the universe's large-scale structures. The discovery of this particular galaxy is particularly significant in this context because it challenges our understanding of how galaxies evolve. According to traditional models, galaxies should have formed gradually over time, with smaller galaxies merging to create larger ones. But this galaxy appears to have formed much faster than anticipated, raising questions about how galaxies can take shape so quickly in the early universe. Could this galaxy be a rare example of an unusually rapid process of galactic formation, one that bypassed the more gradual evolution we expected? If so, this discovery has profound implications for how we think about the birth of galaxies and the formation of complex structures in the universe. Moreover, the rapid formation of this galaxy may suggest that the conditions in the early universe were more conducive to the creation of large structures than we previously thought. Perhaps the presence of dark matter, combined with the ionizing radiation from the first stars, created an environment where gas could collapse more easily and stars could form more quickly. This could explain why this galaxy appears to have developed so rapidly. It could also mean that galaxies formed under different conditions than we assumed, perhaps following different pathways toward complexity. Another important factor in the formation of complex structures is the role of mergers. Galaxies are not static entities. They are dynamic systems that evolve over time, often through interactions and collisions with other galaxies. These mergers can lead to dramatic changes in a galaxy's structure, size, and shape. For example, when two smaller galaxies collide, their gas can be compressed, triggering a burst of new star formation. At the same time, the merging galaxies may undergo gravitational interactions that rearrange their stars and gas, leading to the creation of new structures. This process of galactic merging has been a key driver of cosmic evolution, contributing to the formation of the large, well-structured galaxies we see today. The early universe, with its small, irregular galaxies, was a particularly active time for mergers. In fact, many of the early galaxies likely grew by merging with other small galaxies. These mergers would have been violent and chaotic, but they would also have contributed to the growth and development of the universe's larger structures. The discovery of this galaxy, which seems to have formed so rapidly, raises the possibility that it could have been shaped by such interactions. If this galaxy underwent a series of mergers early in its history, it could explain its relatively advanced structure despite its youth. As galaxies grew and evolved, they began to interact with their surrounding environment, shaping the large-scale structure of the universe. Over time, galaxies formed into clusters, which were the building blocks of even larger structures called superclusters. These superclusters are the largest known structures in the universe, containing thousands of galaxies bound together by gravity. The formation of superclusters was the result of the same gravitational forces that shaped galaxies, but on an even larger scale. These enormous structures, in turn, influenced the movement and behavior of galaxies within them, leading to further interactions and mergers. The study of cosmic structures like superclusters is essential for understanding the evolution of the universe. While galaxies are the fundamental building blocks of the cosmos, they do not exist in isolation. They are part of a vast and interconnected web of matter, with gravitational forces shaping their interactions. This web is what gives the universe its large-scale structure and is key to understanding how galaxies and other cosmic structures formed and evolved over time. The rapid formation of this newly discovered galaxy provides a unique opportunity to study the mechanisms that drive the birth of complex structures in the universe. By analyzing its composition, age, and structure, scientists can gain new insights into the processes that led to its creation. This galaxy may offer a window into the early stages of galactic formation, revealing details about how galaxies form, merge, and evolve in the primordial universe. In conclusion, the emergence of complex structures in the universe is a fascinating and ongoing process, shaped by the forces of gravity, dark matter, and radiation. The birth of galaxies, stars, and other cosmic objects is a critical part of the story of the universe, and the discovery of this rapidly forming galaxy challenges our understanding of how these structures evolve. Whether through mergers, the influence of dark matter, or the effects of the first stars, galaxies and other cosmic structures continue to form and evolve, revealing the intricate beauty of the universe's ongoing evolution. As we continue to study these complex systems, we move ever closer to understanding the fundamental forces that have shaped the cosmos. As we delve deeper into the cosmic dance of galaxy formation, one of the most profound and dynamic processes that shape the universe is the phenomenon of galaxy mergers. These cosmic collisions have been central to the evolution of the universe from the very beginning, playing a key role in the birth, growth, and transformation of galaxies. The discovery of this extraordinary galaxy, with its rapid formation and unique characteristics, brings the topic of galaxy mergers into sharper focus, forcing us to reconsider the role these cosmic events play in shaping the galaxies we see today. In this section, we will explore the complex and often violent nature of galaxy mergers, how they contribute to the growth of galaxies, and the long-term effects they have on the structure of the universe. Galaxy mergers are not rare events. In fact, they are an integral part of cosmic evolution. Galaxies do not exist in isolation. They are part of a vast, interconnected network of matter that is constantly interacting through gravitational forces. These interactions result in galaxies merging with one another, often in spectacular and chaotic events that can dramatically alter the course of their development. In the early universe, galaxy mergers were much more common than they are today, primarily because galaxies were smaller, more numerous, and closer together. As the universe has expanded and matured, galaxy mergers have become less frequent, but they remain a driving force behind the evolution of many galaxies, including our own Milky Way. The process of a galaxy merger is complex and can unfold over billions of years. When two galaxies collide, their stars do not usually collide directly due to the vast distances between them. However, the gravitational forces at play during the merger cause the gas, dust, and dark matter within the galaxies to interact in profound ways. This interaction can lead to the compression of gas, triggering bursts of star formation, and in some cases, the creation of new structures like star clusters and nebulae. The merger can also result in the formation of a more massive galaxy, as the combined mass of the two galaxies creates a larger, more complex system. One of the most significant outcomes of galaxy mergers is the transformation of the galaxies involved. As two galaxies collide, their original shapes are often distorted and reshaped. A spiral galaxy might be transformed into an elliptical galaxy, or two irregular galaxies may merge to form a more structured, well-defined system. These changes can have long-lasting effects on the galaxy's structure, size, and even its future evolution. The collision can also trigger a series of internal processes, such as the activation of supermassive black holes at the centers of the galaxies, which can dramatically alter the behavior of the entire galaxy. For example, when two galaxies merge, their central supermassive black holes, which reside at the heart of most large galaxies, may eventually merge as well. This process, known as a black hole merger, can result in the release of vast amounts of energy in the form of gravitational waves, ripples in spacetime that carry information about the most extreme events in the universe. These black hole mergers are one of the most fascinating and mysterious aspects of galaxy collisions, and they have been the subject of intense research in recent years. The energy released in these events can also influence the surrounding galaxy, triggering new cycles of star formation or even quenching the galaxy's ability to form stars if the central black hole becomes highly active. The impact of galaxy mergers is not limited to the galaxies involved. These events can also affect the larger structure of the universe. When galaxies merge, they are not only combining their stars and gas but also their dark matter. Dark matter, which makes up a substantial portion of the mass in the universe, plays a crucial role in galaxy formation and evolution. The gravitational influence of dark matter during a merger can help shape the resulting galaxy and its surrounding environment. In some cases, galaxy mergers can lead to the creation of galaxy clusters, massive groups of galaxies bound together by gravity. These clusters are among the largest known structures in the universe and can contain hundreds or even thousands of galaxies. The formation of galaxy clusters is a key aspect of the large-scale structure of the universe, and it is heavily influenced by the process of galaxy mergers. The discovery of this newly identified galaxy, with its rapid formation and unexpected characteristics, forces us to reconsider the role of mergers in the evolution of galaxies. Could it be that this galaxy's unusual characteristics are the result of an early rapid merger event? Given that the universe was much denser in the past, it is possible that this galaxy formed through a series of mergers, triggering its accelerated growth. This scenario would help explain why this galaxy appears so mature, with a well-developed structure and the potential for rapid star formation. Rather than following the slow, gradual process of isolated galaxy growth, this galaxy could have been shaped by the gravitational interactions of multiple smaller galaxies merging together in a short period of time. Galaxy mergers can also provide valuable insights into the fundamental processes that govern the evolution of the universe. By studying the effects of these mergers on the galaxies involved, scientists can learn more about the role of gravity, dark matter, and gas in shaping cosmic structures. The study of galaxy mergers can also help to refine our understanding of the timescales involved in galaxy formation. While the traditional view of galaxy formation suggests that galaxies grow over billions of years, mergers challenge this assumption by showing that galaxies can form much more rapidly under certain conditions. If this newly discovered galaxy formed in part through a series of mergers, it could represent a new type of galaxy formation, one that is driven by rapid, intense interactions rather than slow, steady growth. The role of galaxy mergers in the creation of supermassive black holes is another fascinating aspect of these events. When galaxies merge, their central black holes often come into close proximity, eventually leading to a merger of the black holes themselves. This process, which takes millions to billions of years, can release immense amounts of energy in the form of gravitational waves, as well as electromagnetic radiation such as X-rays and gamma rays. The merger of supermassive black holes is thought to be a key driver of active galactic nuclei, AGN, regions of intense radiation at the centers of galaxies that are powered by the energy released by the black holes. The discovery of this new galaxy might offer important clues about the role of black hole mergers in the evolution of galaxies and the creation of AGN. The study of galaxy mergers also sheds light on the broader process of cosmic evolution. Over the course of billions of years, galaxies have interacted, merged, and evolved, resulting in the large-scale structures that we observe today. These mergers are a natural consequence of the way the universe is structured. Galaxies are gravitationally bound to one another, and over time, they will inevitably collide and merge. Understanding the frequency and nature of these events can help scientists refine their models of the universe's history and predict how galaxies will continue to evolve in the future. The discovery of this galaxy, with its rapid formation and unexpected features, highlights the ongoing dynamism of the universe and the central role that mergers play in shaping cosmic evolution. In conclusion, galaxy mergers are one of the most significant forces driving the evolution of the universe. These cosmic collisions are not just the events that shape individual galaxies. They are the building blocks of the large-scale structure of the cosmos. From the formation of star clusters to the creation of supermassive black holes and galaxy clusters, mergers have far-reaching effects that continue to shape the universe we observe today. The discovery of a galaxy that appears to have formed rapidly and unexpectedly may be a direct result of such a merger, offering a new perspective on how galaxies grow and evolve over time. As we continue to study these extraordinary events, we will gain deeper insights into the fundamental forces that govern the universe, further enriching our understanding of the cosmic story. At the center of many galaxies lies one of the most enigmatic and powerful forces in the universe, the supermassive black hole. These massive, invisible objects, which can weigh millions to billions of times the mass of our Sun, play a central role in the formation, evolution, and behavior of galaxies. The discovery of this newly identified galaxy, with its unique characteristics and rapid formation, provides an intriguing opportunity to explore the influence of supermassive black holes on galactic development and the overall structure of the universe. Supermassive black holes are thought to reside at the heart of most large galaxies, and their presence has a profound impact on the galaxies in which they are found. Their formation is still not fully understood, but one prevailing theory suggests that they form early in a galaxy's history, possibly from the collapse of massive gas clouds or from the merging of smaller black holes. Once formed, supermassive black holes begin to accrete vast amounts of matter, including gas, dust, and even stars. This process generates immense gravitational forces, which can shape the surrounding galaxy, influence star formation, and even affect the galaxy's overall structure. The discovery of this galaxy and its rapid growth raises intriguing questions about the role of its central black hole. Is it possible that the galaxy's quick formation was influenced by the gravitational pull of a supermassive black hole? It's known that the presence of a supermassive black hole can trigger star formation in its vicinity by compressing gas clouds and generating immense energy through the process of accretion. In some cases, the energy released by a supermassive black hole can prevent further star formation by blowing away surrounding gas and dust. This phenomenon is known as feedback, and it can have a significant impact on the evolution of the galaxy, potentially regulating its growth and influencing the types of stars that form. Moreover, the interaction between a galaxy's supermassive black hole and the surrounding gas can lead to the creation of powerful jets of energy. These jets, composed of charged particles traveling at nearly the speed of light, can extend far beyond the galaxy itself, influencing the surrounding intergalactic medium. The energy released by these jets can have a dramatic effect on the galaxy's environment, heating gas clouds, triggering the formation of new stars, or even halting star formation altogether. This feedback loop between the black hole and its galaxy can help to shape the overall development of the galaxy, influencing its size, shape, and rate of star formation. As we explore the evolution of this newly discovered galaxy, it is essential to consider the role that its supermassive black hole may have played in shaping its rapid formation. While the exact mechanisms behind galaxy formation are still not fully understood, the presence of a powerful central black hole may have accelerated or influenced the galaxy's growth. Whether through its gravitational pull, its feedback effects, or its ability to regulate star formation, the supermassive black hole at the heart of this galaxy may have played a crucial role in the development of this cosmic structure. By studying this galaxy and its black hole, scientists can gain valuable insights into the complex relationship between supermassive black holes and the galaxies that house them, shedding light on the fundamental processes that drive the evolution of the universe. The discovery of this extraordinary galaxy challenges many of the long-held assumptions about galaxy formation and evolution, opening up new avenues of exploration for astronomers and cosmologists alike. As we stand on the cusp of understanding how such a galaxy could form so rapidly and early in the universe's history, the implications for future research are vast. This discovery could drive a re-evaluation of many fundamental aspects of astrophysics, from the processes governing galaxy assembly to the role of dark matter and dark energy in cosmic evolution. It also invites new questions about the nature of the universe in its infancy and how the first galaxies laid the groundwork for the complex structures we observe today. In this section, we will explore the potential directions that future research could take, spurred by the discovery of this galaxy. First and foremost, the discovery raises profound questions about the timeline of galaxy formation. Traditional models suggest that galaxies grew slowly over billions of years, gradually assembling through mergers and accretion. However, the rapid formation of this galaxy, seemingly in defiance of these models, calls into question whether the early universe had conditions more conducive to faster galaxy formation than previously believed. Future research will likely focus on revisiting models of galaxy growth to determine whether there are mechanisms we have yet to fully understand, perhaps related to the interplay of radiation, gas dynamics, and dark matter, that allowed for such rapid galaxy assembly. Additionally, this discovery presents an opportunity to refine our understanding of cosmic reionization, the period when the first stars and galaxies ionized the surrounding hydrogen gas, making the universe transparent to light. If this galaxy formed during the tail end of the reionization epoch, it could provide a crucial window into how galaxies formed and evolved in the early universe, offering insights into the precise role of radiation and gas interactions. Further studies of the galaxy's composition, particularly its age and the types of stars it contains, will likely provide critical data on the conditions of the universe at the time of its formation. These insights could reshape our understanding of how cosmic reionization influenced the growth of galaxies and whether such galaxies were more common than previously thought. Another area ripe for exploration is the role of supermassive black holes in the formation of such early galaxies. The discovery raises questions about the potential influence of supermassive black holes in galaxies that are still forming, and how their activity might shape the surrounding environment. It is possible that the central black hole of this galaxy played a role in accelerating its growth or even quenching star formation at certain points. Research into the feedback mechanisms between galaxies and their supermassive black holes will be crucial in understanding how galaxies evolve, particularly in the early stages of their formation. The role of dark matter also deserves further investigation. Dark matter remains one of the most elusive and mysterious components of the universe, and its influence on galaxy formation is still not fully understood. This discovery may offer new clues about the distribution of dark matter in early galaxies and how it interacts with ordinary matter. Understanding the relationship between dark matter and galaxy formation could lead to breakthroughs in our understanding of both dark matter and the fundamental forces governing the universe. Finally, the discovery of this galaxy opens up the possibility of finding more such galaxies in the distant universe. With advancements in telescope technology such as the James Webb Space Telescope (JWST), astronomers will be able to peer even deeper into the cosmos, possibly uncovering more early galaxies that challenge current theories. This will likely lead to a wealth of new data, providing a clearer picture of the universe's formative years and helping to refine our understanding of cosmic evolution. In conclusion, this discovery is not just a fascinating find, it is a catalyst for a new era of exploration in cosmology. As researchers dive deeper into the study of this galaxy and others like it, the answers they uncover will reshape our understanding of the universe, providing new insights into the origins of galaxies, stars, and the cosmos itself. The road ahead is full of exciting possibilities, and this discovery is just the beginning of a much broader journey into the mysteries of the early universe. As we delve deeper into the mysteries of the universe, it becomes increasingly clear that the more we discover, the more we realize how much we don't know. The discovery of this extraordinary galaxy, with its unexpected characteristics and rapid formation, raises a multitude of unanswered questions that could revolutionize our understanding of cosmic evolution. In this section, we turn our attention to these questions, exploring the unknowns that persist despite our best efforts to understand the origins of galaxies and their evolution. One of the most pressing questions raised by this discovery is how such a galaxy could form so quickly in the early universe. According to current models of galaxy formation, galaxies should develop gradually over billions of years, with small galaxies merging to form larger ones. Yet, this newly discovered galaxy seems to have bypassed this slower, more gradual process, growing rapidly and achieving a relatively advanced structure far earlier than anticipated. Could this rapid formation be a result of some unknown process or condition in the early universe? Or is this galaxy a rare anomaly, challenging our understanding of the typical path galaxies take as they evolve? Another key question revolves around the relationship between the galaxy and its central supermassive black hole. Supermassive black holes are known to influence the evolution of their host galaxies, regulating star formation and determining the overall growth of the galaxy. But how exactly do these black holes affect their galaxies in the early stages of formation? The energy released by the accretion disks around supermassive black holes, combined with the outflows and feedback mechanisms they generate, could have significant effects on the surrounding galaxy. Could the rapid formation of this galaxy be due to an unusually active or early forming supermassive black hole at its center? And if so, what does that tell us about the processes that govern black hole growth and galaxy evolution? Furthermore, the role of cosmic winds and radiation in shaping this galaxy's development remains an area of great interest. Cosmic winds, driven by supernovae, stellar winds, and the activity of black holes, can drastically alter the structure and behavior of a galaxy. Could these winds have played a critical role in the rapid growth of this galaxy? How might the interplay between the galaxy's central black hole, the winds from massive stars, and the surrounding intergalactic medium have influenced its rate of star formation and overall development? These are the kinds of questions that are essential for understanding the dynamics of galaxy formation, yet they remain unanswered for this galaxy in particular. The discovery also begs the question of whether this galaxy represents a new class of galaxies that formed under different conditions than the ones we are familiar with. Could it be that this galaxy, with its unique characteristics, holds the key to understanding how galaxies can form faster and in more complex ways than previously thought? Or is this galaxy an outlier, an exceptional case that simply happens to defy our current models? The answer to this question could have profound implications for how we view the broader process of cosmic evolution and galaxy formation. Ultimately, the unanswered questions surrounding this galaxy remind us of the vastness of our ignorance. As much as we have learned about the universe, there is still so much left to discover. This galaxy, with its enigmatic nature and rapid formation, opens a new chapter in our quest to understand the origins and evolution of galaxies. And as we continue to study it, we may uncover answers that not only illuminate the mysteries of this particular galaxy but also unlock new insights into the fundamental workings of the universe itself. As we peer deeper into the universe, there's a mysterious force that we know exists but cannot see. Dark matter, a substance that makes up about 27% of the universe, remains one of the greatest cosmic mysteries. Unlike regular matter, dark matter does not emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its presence is undeniable. It exerts a gravitational influence on galaxies, clusters, and even the entire large-scale structure of the universe. In this section, we explore the pivotal role dark matter plays in the formation and evolution of galaxies, including the newly discovered galaxy that has caught the attention of astronomers. Dark matter's influence on galaxies is profound and far-reaching. It acts as the unseen scaffold around which galaxies form. Unlike the visible matter, stars, gas, and dust, that we can observe directly, dark matter is spread throughout the universe in vast halos that surround galaxies. These halos are invisible but crucial to galaxy formation. Without the gravitational pull of dark matter, galaxies would not be able to coalesce and form the structures we see today. In fact, it is the dark matter halos that provide the necessary gravitational framework for the gathering of normal matter, enabling stars and galaxies to form in the first place. The role of dark matter is particularly important in the early stages of galaxy formation. In the universe's infancy, galaxies were much smaller and less structured than the massive systems we observe today. Dark matter played a critical role in drawing gas and dust together to form the first galaxies. The gravitational pull of dark matter acted as a seed, drawing ordinary matter toward it, and this matter eventually coalesced to form the stars and galaxies that populate the universe. This process is thought to have been most active in the early universe, when dark matter was far more influential in shaping the growth of galaxies. This new galaxy, which has formed at a rapid pace, could very well be a result of these early processes in dark matter-driven galaxy formation. Given its unusual characteristics and rapid development, it's plausible that its evolution has been significantly influenced by the surrounding dark matter halo. The gravitational influence of dark matter may have contributed to its quick assembly, helping to pull in gas and material necessary for star formation. In addition, dark matter may also influence the shape and structure of this galaxy. As dark matter interacts gravitationally with the galaxy, it can affect the galaxy's morphology, including its overall size, shape, and the distribution of its stars. Dark matter also plays a significant role in the long-term evolution of galaxies. It's thought that as galaxies grow and merge over time, the dark matter halos surrounding them will also evolve. When galaxies collide, their dark matter halos often interact, and in some cases they may even merge, leading to the formation of larger galaxies. These mergers, driven by the gravitational effects of dark matter, are a key factor in the growth and evolution of galaxies. The newly discovered galaxy could be part of a larger cosmic structure that will continue to evolve through dark matter interactions over billions of years. In conclusion, dark matter is not just a passive force but a key architect in the formation, growth, and evolution of galaxies. The influence of dark matter is felt from the earliest stages of galaxy formation, where it provides the necessary gravitational pull for normal matter to come together and form stars and galaxies. Over time, dark matter continues to shape the evolution of galaxies, particularly through its role in galaxy mergers and large-scale cosmic structures. As we study galaxies like the newly discovered one, we gain more insight into the enigmatic role that dark matter plays in the cosmos, helping us to unravel one of the universe's most profound mysteries. Dark matter, an elusive and invisible substance, is one of the greatest mysteries of modern cosmology. Despite its name, dark matter does not emit, absorb, or reflect light, making it virtually impossible to detect directly. Yet, its presence is inferred by its gravitational effects on visible matter, such as stars, gas, and galaxies. It is thought that dark matter makes up about 27% of the total mass-energy content of the universe, far surpassing the visible matter, which constitutes only about 5%. The remaining 68% is believed to be made up of dark energy, a mysterious force driving the accelerated expansion of the universe. Understanding dark matter is crucial for explaining how galaxies form, evolve, and cluster. As astronomers continue to study galaxies like the one at the heart of this discovery, dark matter's role in shaping these structures becomes increasingly clear. Dark matter is believed to have played a pivotal role in the formation of the first galaxies. In the early universe, the gravitational pull of dark matter was responsible for the clumping of gas and dust, which eventually led to the formation of stars and galaxies. Unlike ordinary matter, which interacts through electromagnetic forces, dark matter interacts only via gravity and possibly weak nuclear forces, making it invisible and undetectable by conventional means. This lack of interaction with light and radiation is why dark matter cannot be observed directly. However, its gravitational effects on visible matter are profound. In the early stages of galaxy formation, dark matter clumps together into what are known as dark matter halos. These halos provide the gravitational foundation for galaxies to form and grow. In a sense, dark matter acts as the scaffolding upon which galaxies are built. The dark matter halos exert a strong gravitational pull, attracting gas and dust from the surrounding environment. As this gas falls inward, it begins to cool and condense, eventually forming the stars and other visible matter that make up the galaxy. The presence of dark matter is crucial for holding galaxies together, as its gravitational influence provides the necessary mass to prevent the galaxy from flying apart due to the motion of its stars and gas. Without dark matter, the gravitational pull of the visible matter alone would not be sufficient to keep a galaxy intact. In fact, many galaxies would not exist in their current form without the presence of dark matter. In addition to its role in galaxy formation, dark matter also influences the large-scale structure of the universe. As dark matter clumps together in the early universe, it forms the cosmic web, a vast network of interconnected filaments of dark matter that shape the distribution of galaxies across the cosmos. This web-like structure is thought to have influenced the locations and movements of galaxies, guiding their growth and evolution. The interactions between dark matter halos and the visible matter within galaxies also help to determine the galaxy's size, shape, and overall structure. For example, galaxies with more massive dark matter halos tend to be larger and more stable, while galaxies with less dark matter may be smaller and more prone to disruption. The study of galaxies like the one in this discovery provides valuable insights into the role of dark matter in the early stages of galaxy formation. If this galaxy formed rapidly, as its features suggest, dark matter could have been a crucial factor in its growth. The dark matter halo surrounding this galaxy would have provided the necessary gravitational foundation for the rapid accumulation of gas and the subsequent formation of stars. Understanding how dark matter influenced the formation of this galaxy could offer key insights into the larger processes that govern galaxy formation and evolution in the early universe. In conclusion, while dark matter remains one of the greatest mysteries of modern physics, its influence on galaxy formation is undeniable. Dark matter provides the gravitational foundation for galaxies, guiding the collapse of gas into stars and helping to shape the structure of galaxies. It also plays a key role in the large-scale structure of the universe, influencing the distribution and movement of galaxies across vast cosmic distances. As we continue to study the galaxies formed in the early universe, the role of dark matter in their formation and evolution will remain a critical piece of the puzzle. Understanding dark matter is essential not only for explaining the formation of galaxies but also for unraveling the deeper mysteries of the universe itself. As we look toward the future of cosmic exploration, the discovery of this remarkable galaxy provides an exciting glimpse into the possibilities that lie ahead. With each new discovery, We are not merely uncovering the history of the universe. We are charting the course for future explorations that could answer some of the most profound questions about the cosmos, our place in it, and the forces that govern its evolution. The discovery of this galaxy, which challenges our existing models of galaxy formation and evolution, is a crucial stepping stone in the ongoing journey of cosmic exploration. It raises new questions, prompts further research, and opens the door for a deeper understanding of the universe. The rapid formation of this galaxy, its unique features, and the clues it provides about the early universe highlight the extraordinary capabilities of the next generation of telescopes and space observatories. The James Webb Space Telescope, JWST, with its unparalleled sensitivity and resolution, has already begun to revolutionize our understanding of distant galaxies. As we continue to explore the universe through the eyes of JWST and other next-generation instruments, we are poised to uncover even more galaxies that challenge our current models of cosmic evolution. This is just the beginning of an era in which the boundaries of our knowledge are continually pushed back, and the universe is revealed in ever greater detail. The implications of this discovery extend far beyond the study of galaxies. It is a reminder of the complexity and dynamism of the universe, where each new discovery has the potential to shift the paradigms that we rely on to understand the cosmos. As we delve deeper into the mysteries of galaxy formation, the role of supermassive black holes, the effects of dark matter, and the processes of reionization, we are also uncovering the broader story of the universe's evolution. Each galaxy we observe serves as a snapshot of a specific moment in time, a key piece of the puzzle that, when put together, will give us a more complete picture of the universe's history and its future trajectory. Looking ahead, one of the most exciting aspects of cosmic exploration is the possibility of discovering even more distant galaxies, some of which may be on the cusp of formation or could even be in the process of merging. These discoveries could provide vital insights into the early stages of galaxy formation and offer clues about the processes that led to the creation of the first stars, black holes, and galaxies. Furthermore, as we study the atmospheres of exoplanets around distant stars, we may eventually uncover signs of life, deepening our understanding of the conditions necessary for life to thrive in the universe. The study of early galaxies also offers the potential to address some of the most fundamental questions in cosmology, such as the nature of dark matter and dark energy. These two enigmatic forces account for the vast majority of the universe's mass and energy, yet their exact nature remains elusive. By studying the ways in which galaxies form and evolve, scientists hope to uncover clues that will lead to a better understanding of these mysterious components of the cosmos. Could dark matter play a more active role in galaxy formation than we currently understand? What role does dark energy play in the accelerated expansion of the universe, and how does it affect the growth of galaxies? These questions represent the frontier of cosmic research, and each new discovery brings us one step closer to answering them. Another key area of exploration lies in understanding the interaction between galaxies and their surrounding environments. Galaxies do not exist in isolation. They are part of larger cosmic structures such as galaxy clusters and the vast cosmic web that connects galaxies across the universe. The discovery of galaxies like the one at the heart of this study allows us to probe the interactions between galaxies, including the effects of galactic mergers, the transfer of gas and dust, and the feedback mechanisms between galaxies and supermassive black holes. These interactions shape the evolution of individual galaxies and the larger-scale structure of the universe, offering us a more nuanced understanding of how the cosmos is organized and how it continues to evolve. As we look further into the future, the quest to explore the universe will undoubtedly become more sophisticated and more ambitious. New technologies and innovations in space exploration will allow us to peer deeper into the universe's past and explore distant galaxies, stars, and planetary systems with unprecedented clarity. Projects such as the construction of next-generation space telescopes and the search for extraterrestrial life through advanced probes will propel humanity into an era of cosmic discovery that we are only beginning to imagine. In conclusion, the discovery of this galaxy is not just an isolated event. It is part of a broader narrative of cosmic exploration that continues to unfold. Each discovery builds upon the last, reshaping our understanding of the universe and inspiring new questions and avenues of research. As we continue to push the limits of what is possible in space exploration, we are bound to uncover more mysteries and revelations that will shape our understanding of the universe for generations to come. The future of cosmic exploration is limitless, and with every new discovery, we are one step closer to unlocking the secrets of the cosmos.